Alright, here we see two pictures. Now in most of my classes I will use the right hand rule which is shown here. Now the left side one, this one is talking about the four fingers. These four fingers are in the direction of the magnetic field. So whenever I am using the right hand rule, whichever the direction the magnetic field is shown or expected, your four fingers I expect you to stretch in that direction of the magnetic field. Then if we are dealing with the current carrying wire, right, let me say if there is a wire, in this case we have the magnetic field going to the left side like this. Okay, so let us assume some magnetic field going in this way, and then in this magnetic field we have placed some current carrying conductor like in this direction. So it is carrying some current in that direction. Then because it is carrying the current in that direction, now it will experience a force in the direction shown. Like in this case the wire will experience force away from your palm, like this is your palm, and the force is coming out of the page like this. So if it is exactly perpendicular, like the wire is perpendicular to the flat on the screen and the magnetic field is also flat along the screen, then the force on this wire will be perpendicular to the screen coming out of the page. If at all, if the current was going in the downward direction, then the force will be into the page. Right, this is about the force on a current carrying wire which is placed in a magnetic field. Right, so either the current carrying wire, or on the right side we see the same magnetic field which is stretched to the left. Right, all the four fingers are stretched to the left, right, and the thumb finger is pointing towards in the direction where the positive charge is moving. Right, if the positive charge is moving in the magnetic field, that will experience force away from your palm, upper surface of your palm. Now if at all, if it is a negative charge moving upwards instead of positive, if it is a negative charge, then the force will be in opposite direction, like the force will be away from in this direction, like it will be away from your back side of your palm. So in all my explanations or in the classes, I will be using this right hand rule to explain you the direction of the forces or direction of the magnetic field movement and all. Right, so whenever, if at all, if the magnetic field is going into the plane, then I will show that your four fingers should be going into the page like this. Right, and these are the four fingers that are going into the page along with the direction of the magnetic field. And if it is a charged particle which is moving to the right, so I will draw your thumb in this direction. So this is your thumb direction to the right. Then when you stretch your right hand so that your four fingers go into the page of the screen and your thumb points in the direction of the charged particle, then if this charged particle is positive, then your upper palm, the palm's upper surface is in this above these X marks, so there will be a force in the upward direction. Right, so there will be a force in the upward direction. This is the direction of the force, and you have the magnetic field direction showing with the four fingers, your four fingers, and your thumb is showing the movement of the positive charge. If it is a negative charge, if this is a positive charge force, if it is a negative charge moving in that direction, then the force will be in the opposite direction. For negative charges, if the negative charge is moving, then the force would be opposite direction. Right, so as I said, if the magnetic field is going into the page, I will show with the four cross marks. If at all, if the magnetic field is coming out of the page, then I will show with four circles with representing the tips of your four fingers and whichever the direction the thumb is pointing. Now according to this one, your thumb should be pointing either to the left or to the right. So let us say if in this case magnetic field is coming out of the page, okay, and your field, the charged particle, is moving to the left. Okay, so you need to adjust your right hand in that direction, so it should be almost going backward from your face. Like at your face, if you lift your hand in that direction, the four fingers will be pointing backwards and your thumb will be pointing towards your left, right? And then depending upon the positive charge or negative charge, the force on the charged particle will be either away from your upper surface of the palm or away from the lower surface your palm. For positive charges, force will be away from the upper surface of your palm. For negative charges, force will be away from the lower surface of the palm. So I want you to remember this, and whenever I use, I want you to make use of this introduction part. Here we see the arrangement for conducting rod. The red color one is placed on a conducting U-shaped loop. This is a U-shaped loop. U-shaped loop is this one, the black one. So on that U-shaped conducting loop, we have placed a conducting rod of length L, right? Now here let us assume that there is some magnetic field going into the page. Now this is the direction of the actual magnetic field, that is across the page, we can say, right? So I am just drawing few cross marks here to show that there is the magnetic field going into the page, right? So all the way throughout the page you can assume that the magnetic field is going into the page itself, right? Now here I have drawn two rods. Initially, when t equals to 0, the rod is here. T equals to 0, this is the position of the rod. So after a time t equals to delta t, some t seconds, where the delta t time have passed, during this time the rod was being pushed towards right. Now we are pushing the rod or pulling the rod in this direction, so that the rod moves with v meters per second. So because it is traveling towards right side with v meters per second, and after a delta t seconds of time, it is at the new position here. Okay, so in this time it has traveled this much distance. So this distance is equal to the speed, which is v, multiplied by the time, which is delta t. So v times delta t is the distance it has traveled from here to the next position there. So because the rod is moving to the right, and as we can see, initially the closed loop was from, like it is within this A, B, C, D. The closed loop was A, B, C, D only, that much area. But in the new position, by the time the rod has moved all the way from here to there, the area of this A, B, C, D was increasing. So because the area was increasing, there is a change in the flux. So the flux is changing here. That means in the closed loop there is a change in the flux. The amount of magnetic field lines within the area of the loop are increasing, right? That's the reason we can say that magnetic flux is increasing, because of the increasing in the area, right? Okay, so according to Faraday's law, as we have already seen in previous lectures, induced EMF is equal to the rate of change of magnetic flux. So d phi over dt. I am ignoring the negative sign here because we are not interested in the direction of that. We are only looking at the magnitude of the induced EMF. So what is the change in magnetic flux? The change in magnetic flux is because of the change in the area. The area was changing as the time was passing from t to delta t time, right? So the flux is given by BA cos theta actually, but because the theta is 0 here, because the perpendicular drawn to the area of the loop is out of the page, so the perpendicular drawn to the page is this, out of the page, okay, and the magnetic field is into the page, or perpendicular the drawn to the surface is also, you can consider. here cos theta is equal to 1 because theta equals to 0. So for our case, phi is given as BA cos theta, where phi is the magnetic flux, and here in this case it is BA cos theta is equal to 1 because cos 0. What is this 0? This is the angle between the magnetic field direction which is going into the page, and I have drawn a cross mark with a different color representing the direction of the normal drawn to the surface. This is the normal drawn to the surface into the page. So both of them are in the same direction. The normal drawn to the surface and the magnetic field are in the same direction. That's why the angle between them is 0. So cos 0 is going to be equal to 1. Then flux through that coil is BA, right? So but our BA is not remaining constant because A is not constant. Then if we bring this BA here, then it becomes d by dt of the flux which is BA. But B here is constant. Our magnetic field, external magnetic field is constant. So that comes out. Then it will be dA over dt. So dA is the change in area over certain time of dt. So what is the change in area here? The change in area is this region of the increase in the area. This region is the change in area. So that change in area, now if we try to find out, that area will be the d, which is this length, times the length of the rod, the length. So our d, which we have calculated, is v times delta t times L. So delta A value is this much. Now substituting this delta A value into this equation, our induced EMF now is equal to B times dA is V delta T times the L over, I have dt. dt is the time taken, so our dt is delta T. So in delta T, then induced EMF equals to this delta T cancels, then we have BLV. So this is the expression for the induced EMF. Okay, we have derived an expression for induced EMF using the Faraday's law of electromagnetic induction, and we have arrived at the induced EMF equals to BLV. This is the equation that we got. The same expression can be derived without using the Faraday's law of electromagnetic induction. Now let us see how we can do that. Because now that, as we have already seen, that as the red color rod is moving to the right, we have seen that there will be some force on the charged particles. Now let me take that red color rod again here. So let us say this is the rod that is moving to the right, and we have the magnetic field passing into the page. Now as we have seen before, so on across this, drawing that magnetic field on either side of that, so that we can assume that the magnetic field is there on either side throughout this. So as this rod is moving to the right, we know that to the right with v meters per second, we can assume that the electrons in the rod are also moving in the right side. All these electrons are moving to the right with the same velocity v meters per second. So because the electrons are moving to the right with v meters per second, I want you to see this picture. According to this picture, as I have given the introduction at the beginning, how am I going to use this? So here the magnetic field, in order to stretch your right hand in the direction of the magnetic field, I want you to keep your right hand pointing all the four fingers like this, going into the page. So when they are going into the page, I will have these cross marks. So your four fingers are going into the page, and the electron, the charged particles, are moving to the right. So I will draw your thumb finger to the right. So this is your thumb direction. Now because from this diagram we can see the force on the positive charges is exerted away or perpendicular in the perpendicular direction to your palm's upper surface when the charged particles are positive. If at all, if they are negative charges, as I have shown, the force will be away from the backside part of your palm. So your upper part of your palm should be like this. This is your upper region and this is your lower region. So the force on these electrons which are moving to the right should be downwards. That means this is the force exerted because of the magnetic field, and this force is given by B Q V sine theta. And this sine theta is the angle between the direction of the magnetic field and the velocity of the charged particles. The charged particles are moving to the right and the magnetic field is into the page. That's why theta equals to 90 degrees. So because theta equals to 90 degrees, sine theta becomes 1. So the magnetic force on the charged particles, on the electrons, is in the downward direction. So electrons are being pushed to the downward direction. So we have the maximum force BQV acting on that, right? So this is the force acting on it. Now when this force is acting on the charged particles, and this will exist as long as the rod is moving to the right with V meters per second. So now this force is doing some work on these charged particles to move them from one end of the rod to the other end of the rod. So our length of the rod is how much? It is L meters. So the amount of work done is given by the amount of force multiplied by the distance through which it is moved. So here the force applied on the charged particles is BQV, and this is moved through a distance of L meters. So we have BQVL as the amount of work done. And now this amount of work done, the work done in moving one charge or one charge of Q, but the induced EMF is considered as the amount of work done per unit charge in moving it from one end of the rod to the other end of the rod. So the amount of work done is BQVL, which we just got before, and per unit charge is Q. Q and Q gets cancelled, so induced EMF should be equal to BVL, which is exactly the same equation that we got here, PLV or BVL. So the same expression is derived without using the Faraday's law of electromagnetic induction. So in both the cases it is, or both the ways you can apply and use. Now let us check our understanding by solving one question which we have here. Now, does a moving airplane develop a large EMF? So if you look at the picture on the right here, this moving airplane is in the Earth's magnetic field, and because it is made up of metal or conducting this thing, so the wings, which are very long enough, do they develop any EMF on them? Is it going to be large or very small, which can be ignored? Let us just check. So here an airplane travels 1000 kilometers per hour in a region where the Earth's magnetic field is about 5 times 10 power minus 5 Tesla and is nearly vertical. So here we are assuming that the magnetic field where the airplane is flying is vertical to the wings, right? So what is the potential difference induced between the wing tips that are 70 meters apart? So let us say this is some 70 meters apart, right? The width of the wings, which is 70 meters, and here we are assuming that the magnetic field, Earth's magnetic field, is vertical to this. So there is Earth's magnetic field which is vertically downwards, and the wings are 70 meters apart, and here because the airplane is coming out of the page, now the wings are moving out of the page. So out of the page is represented by this circle with dot, where the wings are coming out of the page. So the direction of the airplane and the direction of the magnetic field are perpendicular, right? So because it is perpendicular, both the wings motion and the magnetic field are perpendicular, there will be an induced EMF. There will be some force on the conducting these electrons in the conducting material, right? So we'll try to see what is the direction of the force on this moving one. So if it is moving, so we have our 4 fingers to be pointed downwards. So our 4 fingers magnetic field is in the downward direction, and your 4 fingers also should be in the downward direction, as I shown here. This is the magnetic field direction, and your thumb finger should be pointed out. It should be pointed coming out of the page. So that's why a circle with dot. So in this case, if you adjust your right hand like this, your palm's upper surface will be to the right and your palm's backward surface will be to the left. Okay, so because the airplane wings are coming out of the page, then the electrons on that should experience force towards the left. The electrons will experience force towards the left. So automatically we will have some induced EMF by setting up more negative charges over here and more positive charges over the right side. So this has set up some induced EMF. We are going to calculate how much is this induced EMF is going to be, right? So we have already seen that induced EMF for in a moving conductor is given by BLV. So by substituting the values here, the magnetic field is 5 times 10 power minus 5 Tesla times the wings are approximately like 70 meters apart times the velocity. So we will convert that to meters per second. This 1000 kilometers per hour speed is converted into meters per second. So 1000 kilometers per hour is equal to 277.8 meters per second. So I am going to use this meters per second value here. So 277.8, and upon simplifying this we get 97,222.2 times 10 power minus 5, which is equal to 0.97 volts. So the induced EMF across that is not even 1 volt, which can be negligible, which is very, very small. I hope you understood this concept of induced EMF in a moving rod which is placed in a magnetic field, and we will continue on this to know the induced current and magnitude of the induced current. Coming back to this equation, induced EMF equals to BLV, which is developed due to the motion of the conducting rod in the magnetic field. Now as that U-shaped conducting wires, upon that U-shaped conducting wires this rod is placed. So because it is a closed loop, then definitely there will be a induced current also because of the induced EMF. So now what is the direction of this induced EMF? As we have seen that as this red colored rod moves to the right with V meters per second, there will be an induced EMF, and that induced EMF is given by the magnetic field strength times the length of the rod, which is this, and the velocity, the product of magnetic field, the length and the velocity. Fine. Now we know that the rod is also a conducting material, and also the rod which is moving, you can say that it is sliding on this U-shaped conducting wires or conducting rails, we can let us say that they are conducting rails. So because they are conducting rails, and the loop is closed, like as the red colored conducting rod is placed on the rails, we have a closed loop. Let us say that closed loop is named as A, B, C, D. Initially this was a closed loop, and as the BC section was moving to the right, later BC is here after certain time. So during this time is where the induced EMF was developed. Fine. But because it is closed loop and induced EMF is there, because of the induced EMF, there should be some current I that is flowing in the closed loop. So what is the direction of this current and what will be the magnitude of this current? Right? Let us see that. So from Ohm's law, this I is given as, we can calculate that I as the induced EMF or the potential difference over the resistance. Now let R be the resistance of our closed loop. So even though they are conducting ones, they will have certain resistance, right? So let us assume that their resistance is R. So now what is this induced EMF here? That potential difference for us is BLV, which is the induced EMF over R. So this is our expression for I. BLV over R is the expression for the induced current. Fine. But what is the direction of this induced current? If we have to look at the direction of the induced current. Now here both the possibilities are there. Whether the induced current can be in clockwise direction like A, B, C, D, or the induced current can be in anti-clockwise direction like from A, D, C, B, A. So anti-clockwise direction is possible, clockwise direction is also possible. So which one it will? As per the Lenz's law, when induced EMF is developed, that induced EMF produces some induced current, and that induced current should oppose whatever the change that is creating this induced current. So what change is creating this induced current? The increasing magnetic field which is going into the page. Here in this loop area, the magnetic field is going into the page. This is going into the page, and that magnetic field which is going into the page is increasing, right? So the induced current should oppose this increasing magnetic field. So if it has to oppose that increasing magnetic field, then that induced current should develop some magnetic field which opposes the increasing magnetic field. That means there should be some magnetic field that is coming out of the page which will oppose this motion. There should be some induced magnetic field because of the induced current that is coming out of the page. As this magnetic field that is going into the page is increasing, in order to oppose that increment, there should be magnetic field coming out of the page, right? In order for the magnetic field to be coming out of the page, right, what should be the direction of the current? Which direction of the current will give us this magnetic field that comes out of it, right, in this particular situation? So here I want again you to use that right hand thumbs rule which is shown here. If you imagine holding this BC section of the wire as shown in the picture here, like the red colored wire which is having the current going in upward direction. Now if you have to stretch your right hand and hold that BC section in the same way as shown in the figure, then the tips of these fingers, 4 fingers, will be the direction of the magnetic field that is coming out of the page, right? So if we imagine that if you are holding this section of the wire as shown in the picture, we will have the magnetic field that is coming out of the page as shown here, which opposes the increasing magnetic field in the loop area, right? So that means here we need to, as our thumb is stretching towards B here upwards, that means our induced current now is in anti-clockwise direction. So the direction of the induced current is anti-clockwise in this loop as of now, right? So now this induced current, because this induced current is there in the wire, and we also know that this induced current, either it is induced current or normal current, whatever, so the current is current. So now any time when there is current passing in a conductor, around the conductor there will be a magnetic field as shown in the same picture here, right? So that is the magnetic field that is coming out fine here. But if this wire is placed in some external magnetic field, like here the external magnetic field that is applied to the overall coil is going into the page, right? So because this field is going into the page and our wire which is carrying the current in anti-clockwise direction is in that magnetic field and carrying that induced current now because it is moving to the right. So we know that that wire will experience a magnetic force. The force on that wire will be the magnetic field strength times I, the current passing in that wire, and the length of the wire multiplied by sine theta. Now here theta is the angle between the magnetic field direction and the length of the wire. So for us, the magnetic field is going into the page, the external magnetic field, and the length of the wire is perpendicular along the screen. So the direction between them, the angle between them is 90 degrees. So sine 90 equals to 1. So the magnetic force on that wire will be BIL. Fine. This is the magnetic force, maximum magnetic force that is going to act on that red colored wire. But what is the direction of this magnetic force? In order to know that the direction of the magnetic force, again we need to use that right hand rule. I want you to use the picture shown here in order to find the direction of the magnetic force on that wire BC. Right, let us say here the right hand directions are shown here. Now there is slight difference between the picture shown, the directions there, and the situation that we have. In the picture the magnetic field is towards the left, but in our case the magnetic field is going into the page. So your four fingers should be acting into the page in as it is shown in the direction of the magnetic field that we have. So our four fingers of your right hand should be going into the page like this. I am just drawing 4 circles representing your 4 fingers that are stretched towards into the screen. And when you stretch like this, and we already understood that the induced current is in which direction? In the anti-clockwise direction. So in the section BC, the current is going in upward direction. So our thumb finger should be pointed in upward direction, in which direction the current is passing. This is the direction of the current and this is the direction of the magnetic field that we have. Fine. So the place where I wrote B is the back side part of your palm. On the other side, this is the front part or the upper part of your palm here. So now as it is shown here, the force will be perpendicularly away from your palm. So in our situation here, the force should be acting perpendicularly towards the left side. So this must be the direction of the magnetic force. That means as the external agent is exerting some force in towards right. So this is the force exerted by, let us say, by Mr. Jordan, myself. And as I am exerting this force, the induced EMF has developed, and that induced EMF has produced some induced current in anti-clockwise direction, and because that anti-clockwise direction induced current is there, and this wire is the only one which can be movable, and that wire which is carrying this induced current is in the external magnetic field that is pointing into the page, right? So that wire or the section BC is experiencing a force that is opposing the force applied by Mr. Jordan. That means it is exactly equal and opposite to the force applied by the external agent. Now this is something that is required. That means from this we can see the moment when external force applied by Jordan becomes zero, there is no more change in the flux. The moment when there is no more change in the flux, there is no more induced EMF. Automatically further there is no more induced current. Because there is no current in the section BC, and though it is there in the magnetic field of external magnetic field, now it will not experience any force. That means as the external agent force is increasing, the opposing force is also increasing, right? So that whatever the work done by the external agent is shown in the circuit in the form of the electrical energy that is flowing in the circuit, right? So from this video, until now we are able to understand the direction why the induced EMF or why there should be a constant force. Now if at all, if we had mistaken and we considered the current direction is in the clockwise direction, then what will happen? I want you to think. Pause for a minute and then think. Come back. Okay, alright. So, if at all, if we have assumed that the current is going in a clockwise direction, then in the section BC, the current would not be going in the upward direction, but it would be going in the downward direction, right? So our thumb needs to be pointing in the downward direction. So when you stretch your right hand in the same direction and rotate it such that your thumb points in the downward direction, because the current is going in the downward direction, then the external magnetic field will not exert force on that wire in this direction. Rather, it will exert force in opposite direction, like in the towards right side. That means the force now is going to be towards right side. Now, what is the problem if it is this way? The external agent is also exerting force to the right. The moment when the external agent exerts force to the right, there is induced EMF, induced current, and that induced current experiences the magnetic force to the right. That means, if at all, if I had infinite magnetic field like this throughout the space, and if I have infinite length of rods, if I continue like that, then in such a case, I need to only exert some force at the very beginning. A little force will be sufficient. Once that force is given, that is the amount of work that the external agent is doing, very little work. But once that force is there, induced EMF, induced current are generated, magnetic force is also generated, and that magnetic force now starts pushing it to the right. So it continues there, and we will have electrical energy without any further energy required, right? That means we are able to get energy or produce energy without any of the external work done, or with the least amount of work done you can get infinite amount of energy, which is completely against the law of conservation of energy. Now, according to the law of conservation of energy, as we all know, that energy can neither be created nor be destroyed. That means we cannot get energy from nothing. At the same time, energy cannot become nothing. Energy has to be there in some or the other form, or energy can only come from some or the other form of energies. That means this direction, or when the magnetic force is the external magnetic force on the moving conductor acts in the direction of the external agent, we are getting an infinite amount of energy from nothing, which is against the law. That way also we need to check. So automatically we have to see that in whichever the direction the external agent is increasing or exerting the force, the magnetic field should exert a force in opposite direction. So in that way also we must be able to determine the correct direction of the induced current, or we must be able to apply Lenz's law properly and identify the direction of the induced current. Right. Moving on, now we can see that there are these two forces, which is the external agent's force and the magnetic force, which are acting in opposite directions, right? So we need to, even though, let me just clear it off. All right. So as we now understood that the induced current should be in the anti-clockwise direction in this situation. Now let us say then in that case we have two forces acting in opposite direction where the rod is moving in a constant speed or constant velocity. Now that means there is some force exerted by Jordan, and this force multiplied by the velocity with which the conducting wire is moving should be equal to the power or the rate of doing work by Jordan or by the external agent. So now as we have this force exerted by Jordan times the velocity should be equal to the power, and that force we also know that is equal to force exerted by the magnetic field times the velocity, but just it is in opposite direction. So if we look at that force exerted by the magnetic field, we already have a formula for that here, FB equals to BIL, which we have derived. So this expression now becomes BIL times V, right? So now if I rewrite this expression in terms of only B, eliminating that I by substituting for I value in terms of B, I have B times BLV over R is the I value which we have here, right, times LV. So now overall this now becomes B square L square V square over R, which is the power or rate of doing work by the external agent. So if this is the rate of doing work by the external agent, what is happening to this work done by the external agent? That work done by the external agent should somehow show up in the loop itself in some form of the energy. So here we have electrical energy that is passing through the loop, and that electrical energy is dissipating in the loop in the form of heat. So the power dissipated in the loop, which is carrying some current I, is given by Ri square and having some resistance. So the power dissipated in the loop is given by P equals to I squared R. And now if we substitute the value for I in this, it will be BLV over R whole square times R, which gives me B square L square V square R over R square. This R and this square gets cancelled, so we have B square L square V square over R, which is exactly same as what we got here. Now this is the power or rate of doing work by the external agent, and this is the power dissipated in the loop. So both the expressions are equal and are exactly same, which means the work done by the external agent is equal to the work developed or done in the loop, or which transformed into thermal energy. I hope this video is clear enough for you to understand about the motional EMF and the concepts of induced EMF and induced current.